Now their notion of convection relies on buoyancy. Their premise is that moist air is lighter than dry air. And that premise is based on the supposition that moist air contains steam. After that, it's just a matter of doing some simple math. We have the molecular weight of H2O being 18, the average molecular weight of the air, nitrogen and oxygen, being 29, and then we just realized that moist air, even in the most moist air, it makes up maybe 3% of the quantity of the air that's within that volume. And you'll note after you do the math on this, it comes out to being a 1% difference. This one being 99% lighter than this one right here. And that 1% difference is what they are telling you is powering the storms in our atmosphere. That explanation of there being a 1% difference in the weight of air, and that being the power of our atmosphere, has a gigantic flaw. It relies on the existence of steam. Moist air is heavier than dry air, always. There are no exceptions to this rule in our atmosphere, because our atmosphere is too cold to support the existence of steam. Now basically there's two types of people within meteorology or otherwise when it comes to this issue, and that is those who understand it and who are lying, and those who simply don't understand it and just believe it. And so confronted with this confusing information about what water's doing in the atmosphere, and the fact that we still, if we still can't assume it turns to steam, we still don't have any way of explaining how it gets up high in the atmosphere. When you're putting those together, you can kind of understand why meteorologists kind of gave up on this one. They said, hey, let's just assume that it turns to steam, and let's not really look too hard, and we can kind of get away with that explanation, and keep in mind there's no other explanation. And I asked myself, is it possible that H2O has a dual personality? Is there something about it that it can be highly active in one sense, preventing the formation of coming in to form droplets in such a powerful way, and at the same time, but once that's formed, lose its power, and on top of that, might this dichotomy in some way explain some other process as to how it gets up so high in the atmosphere? I did the normal things anyone would do. I went to the internet first of all, and I really got into some research and came across this notion of hydrogen bonding for water, or H2O polarity. And frankly, it was just the fact that this H2O polarity indicated quirkiness. And by that I mean water is associated with a lot of what they call anomalies. In other words, it just does things different than what their models predict it would do. And it seemed to me that there was enough confusion with respect to hydrogen bonding and polarity that maybe this, and the fact that there's all these anomalies, I said, well, maybe there's another anomaly associated that'll explain what I was trying to explain in the atmosphere, explain this dichotomous behavior, and also give us some mechanism as to how water gets up high in the atmosphere. And I looked and looked and looked, and eventually came to the realization that according to what the experts were saying, the answer was firmly no. No, polarity did not, according to their understanding of polarity, it didn't really have the ability to have this dual dichotomy behavior, this strange paradoxical way of that I was noticing, and it didn't have any other capabilities that would allow it to rise up in the air other than, what was already described, which was that if it turned to steam, it would convect. And then I asked myself a pretty big question. I said, what if they're simply wrong? What if they made a mistake on some very fundamental level, and they're so busy trying to fit the pieces of the puzzle together, they didn't realize that they're missing a big piece of the puzzle, or that they've actually got the wrong, two puzzles mixed up, and they're trying to mix them together or something along those lines. So I said, what if they're wrong? And specifically, I was looking at hydrogen bonding. I go, what if there's something about hydrogen bonding that they simply haven't figured out? Hydrogen bonding simply says that the water molecule's shape dictates that this oxygen molecule here sucks down more of the electrons, making this more negative and making these two little Mickey Mouse ears here more relatively positive. And that creates this kind of a hydrogen bond going on here. But that didn't really answer any of my questions. So I wondered if there might be something more going on with hydrogen bonding than just that. And this is what I came up with. I wondered if hydrogen bonds themselves might in some way have something to do with neutralizing the polarity that's in that's in water molecules. And the logic works out as such. Here is a water molecule that has 2 hydrogen bonds on it, and that is the liquid form of water, and that would explain why when water is in a liquid form in the atmosphere, a droplet, let's say, it's relatively passive. It has no more polarity, because that polarity has been neutralized by these 2 hydrogen bonds. And this would be a steam molecule, and of course this would be one that wouldn't really exist in our atmosphere. But because its polarity is so high when there's nothing attached to it, that explains why the boiling point is so high. And then this one right here is what I imagine the surface tension would look like. In other words, this had one molecule attached to it, but it still had some degree of polarity. Note that these numbers in here indicate the polarity. In other words, this had half the polarity of the steam, but since it had some polarity, this was a hard connection. And so that explained how water has this surface tension and the ability to form hard bonds and some degree of electromagnetic activity that I would associate with some kind of a plasma. So I'm referring to this as their polarity coefficients, and I'm saying that polarity coefficient is variable, and it gets neutralized when bonds are complete. It's fully activated only when bonds aren't complete at all, and it's in half polarity coefficient. It's in half polarity when there's only one associated with it. So the next thing I did was started looking into water science. And I was specifically looking for confirmation of the mechanism that I envisioned, this notion that H2O polarity was variable, and that that hydrogen bonds were the mechanism that caused that variation, that caused that polarity to go up and down. Specifically, hydrogen bonds neutralize the polarity. And I actually expected to find it. I expected that this was something that was well understood, and that it was maybe a little bit obscure, but if I was to look hard enough, I would find evidence that substantiated it. But it turns out, not the case. Not the case. I didn't find anything that would suggest, or no one explicitly indicated that any kind of mechanism like this was possible. Now, being a person who is naturally kind of cynical of authority, which I guess in a sense, which is what originally got me to suspect that meteorologists really didn't know what they were talking about in the atmosphere. And And since my research confirmed that, I felt, pretty confident about that. I also suspected, hey, maybe these water researchers really don't, well, maybe they just missed something. Maybe they missed something. So I started looking into polarity, and I kind of already mentioned part of it, which has to do with what they call electronegativity differences. Let me explain that a little bit more explicitly. Now, electronegativity difference, here's a water molecule. It just simply says that this oxygen molecule is more massive and it pulls down electrons onto this molecule here, and making these more positive and this more negative. But a lot of molecules have this ability, and they aren't all polar molecules. And let me give you a perfect example, and that's the methane molecule. It's very similar to the water molecule because it has hydrogen, covalently bonded hydrogen bonds, or covalent bonds with hydrogen atoms. Now, what's different though about the carbon or the methane molecule is that it is not it's not a polar molecule because of the fact that these are all arranged symmetrically. Now, part of the limitations when it comes to explaining something like this is the fact that you have a two-dimensional piece of paper here. In reality, this is a four-dimensional thing, and it involves what they call a tetrahedron. If you were to twist two of these molecules like this, you would see that this is actually a tetrahedron that goes like that. And there's a tetrahedron, you can think of it being a three-sided pyramid with a bottom. It has four corners and four sides. And each one of the corners of the tetrahedron on the methane molecule is filled with a hydrogen atom. Now, the water molecule also has that same underlying template, which is based on what they call the steric number. And there's a whole theory about this called Vesper theory. I suggest looking that up if you're interested in understanding how electrons are arranged in the outer valence shell of the molecules that make up most of our environment, things like oxygen, carbon, nitrogen, those kind of things. Now, with oxygen, a little bit more of a massive molecule, so it attracts more electrons naturally, and here are the two, what they call non-bonding pairs of electrons for the water molecule. And again, if we were to really imagine these things, it would be more of a tetrahedron like this. You would twist these like this. But this is a polar molecule because of the fact that it can't really form covalent bonds down here, whereas this one can, methane can form covalent bonds on all four corners. It therefore is not a polar bond or a polar molecule, a dipole. Now, I started asking myself, though, some rhetorical questions. I said, what if, kind of a thought experiment, I said, what if we were to remove the two hydrogen atoms off of this, artificially in some way? Wouldn't this turn into a polar molecule? And then I took that a step further and I thought, what if these things were actually movable? We can envision the polarity in here actually changing, going up and down. And I took that a step further and I says, well, what about the, if that'll do that here on the, on the methane molecule, on the carbon atom, why wouldn't it do the same thing with oxygen on the water molecule? And why would it even matter whether the bonds that formed down here were covalent or not? As I thought about it, it really wouldn't matter. It wouldn't make any difference at all because it has to do with what's happening to the electrons on here. And the electrons don't know the difference between a covalent bond and a hydrogen bond. And so that kind of answered the questions. You can think of it this way. As hydrogen bonds are formed in water, they neutralize the polarity. So if there's two bonds here, two other H2O molecules come up and form a hydrogen bond right here, the polarity here on this molecule is going to be 0. And if there's 1, the polarity is going to be 2. Which, if you remember, gets right to what we were discussing previously. Zero, 4, 2. And the concept that it all comes down to, and this is the thing I think the people in water sciences missed, is that they may have understood electronegativity differences, and they may have even understood the fact that symmetry, you know, it's hard to believe they don't have some understanding of this being asymmetrical and this being symmetrical, and that being the underlying cause of the H2O polarity. But here's the thing I think they didn't quite take into account. Symmetry is not a constant, it's a variable depending on the degree to which hydrogen bonds are formed. And that answers the question. That tells us why H2O has such unusual behavior in the atmosphere, and of course in all contexts, and why it has, well, let's go over that again. It has the high boiling point. It has the high boiling point because it has that high polarity when it's on an individual basis. It's passive anytime it's in a liquid form. By that I mean its polarity has been neutralized. And that helps us understand another kind of quirkiness of H2O, and that is why it is so fluid. See, when this is zero, these things just kind of float here, these hydrogen bonds. And as they pull away, the polarity would start to return, so they could never quite get away. H2O is in a sense kind of it's a pseudo gas and it's a pseudo liquid, because the more it becomes a liquid by creating a bond here and coming together, the more it zeroes this out, which allows it to float away again. So water really does have kind of a dual personality, and it all comes down to the fact that H2O polarity, or the polarity, is variable. And this is maybe, I think, the most interesting one of all, especially with respect to understanding the possibility that there's any kind of a plasma going on in our atmosphere, and that might explain some of the phenomena like tornadoes and jet streams and such. And since this does allow for a more electromagnetically active and a harder bond, we can now have a mechanism to understand how, when surface area of water in the atmosphere of liquid water is maximized, it produces a more electromagnetically active entity